If you are an engineering or mathematics student, you likely spent time learning how to solve math problems the classic way, using algebra, trigonometry, and calculus to derive exact formulas. But as we move into more advanced engineering problems, these methods don't always work, and we need a different approach. Today we are going to explore the fundamental differences between numerical and analytical methods. This is often the very first topic covered in a numerical analysis course, and understanding this distinction is crucial for knowing which tool to use when you're solving real-world problems. We will begin by breaking down the definitions, walk through a few specific examples where standard math fails us, and look at where and when these methods can be used. Let's start with what you're probably most comfortable with, analytical methods. An analytical method is a mathematical approach that uses logical steps, like those taught in both algebra and calculus, to derive an exact solution in the form of a mathematical formula. When you think of solving for x using pen and paper, you are performing an analytical method. The beauty of this approach is that we can evaluate these derived formulas to produce a perfect solution rather than relying on approximations or guesses. The result is a precise formula that is 100% accurate within the function's domain. Let's look at a simple algebraic example to see this in action. If we have an equation x equals y cubed plus 2, and we want to solve for y, we use symbolic manipulation. We subtract 2 from both sides to get x minus 2 equals y cubed. To isolate y, we take the cubed root of both sides. This gives us a new formula. Y equals the cubed root of x minus 2. But why is this useful? Because this formula is precise. We haven't estimated anything, and we have just rearranged exact truths to find a perfect solution. Now, let's introduce numerical methods. These are mathematical tools that use algorithms and arithmetic to find approximate solutions to math problems. Numerical methods are different to analytical methods in that they are not focused on symbolic manipulation. Instead of hunting for the perfect formula, we use iterative processes. This means that we repeat a calculation over and over again to refine an answer until we reach an acceptable level of error. Let's look at an example to see this in action. Let's say we do not have a computer or a calculator and are asked to find the value of the square root of 2. Well, let's convert this into a better form first. We will square both sides of our equation and we get x times x equals 2. Then, one way we could solve this is begin by guessing values of x and assess how far we are away from 2. Let's make our first guess, x equals 1.5. We test it by squaring it, so 1.5 times 1.5 equals 2.25. Like we said, we're looking for 2, but we got 2.25. So we calculate our error, epsilon 1. The absolute difference of this is 0.25. Let's say that this error is too high for our application, so let's perform another iteration. Like we said, 2.25 was too high, so let's lower our guess to 1.4. We run the algorithm again, 1.4 times 1.4 equals 1.96. We're much closer this time, and if we check the error, we are left with 0.04. For this purpose, let's deem this as acceptable, but this is the essence of a numerical method. We traded a symbolic operation for a sequence of simple arithmetic steps, multiplication and subtraction. That got us closer and closer to the truth. Let's look at some proper examples now, beginning with analytical method examples. Suppose we want to find the area under the curve of x cubed, from x equals 1 to x equals 3. In an analytical approach, we use the power rule. We know that the antiderivative of x cubed is x to the 4th over 4. We can now evaluate this at the upper bound, and at the lower bound and subtract the 2. 3 to the 4th power is 81, and 1 to the 4th power is simply 1. As they have a shared denominator, we can add the 2, and we get 80 over 4, which simply reduces to 20. And here the answer is exactly 20, not 20.001, not 19.999. It's exactly 20. and this is the gold standard of mathematics. It is perfect. We see the same thing with finding roots. Let's say I give you the polynomial x squared minus 2x minus 3 equals 0. And we'll use the quadratic formula for this. You plug in your coefficients, a equals 1, b equals minus 2, c equals minus 3, and we can find the exact roots, which are at x equals minus 1 and x equals 3. And again, these are perfect, and these are exactly the roots. It's not close to these numbers, it is these numbers. So, if analytical method gives us an exact, perfect answer, why do we even need numerical methods? Well, try to integrate this definite integral of e to the power of minus x squared from 0 to 2 using the fundamental theorem of calculus. You can go ahead and try to find the antiderivative, but you're not going to get very far because we actually can't. It's not that you aren't smart enough, it's that there's no elementary antiderivative that exists for this function. This means that you cannot write the antiderivative using standard polynomials, logs, exponential, trig functions, or the like. We can see from our graph on the left that there should be some answer though, as we have an area under the curve. So one way we could go about solving this is using numerical methods. Although we cannot easily find the antiderivative, we can approximate the area under the curve using a concept you likely learned in early calculus courses. Riemann sums are a common lesson taught to introduce calculus, and it is the idea of breaking our area on the curve into smaller little rectangles and then summing the area of those rectangles. So, let's use a version of the Riemann sum called the left Riemann sum. The formula is presented here. The width of the total interval is 2, from 0 to 2. So the width of each rectangle will be 2 over our number of intervals, which we are told is 4, therefore our delta x is 0.5. This is the width of each of our rectangles. Now, we need the heights. For our left Riemann sum, we need to evaluate the function on the left side of each interval to determine the height. I've completed that in this table presented here. Now, we just need to sum them up. So our area is going to approximately equal the sum of our rectangles, so width times heights. Completing this, we get 1.126. Is this an exact answer? No, it has error denoted by the epsilon here. But it is a very good estimate, and crucially, we calculated using only basic multiplication and addition. Something important to note is these are operations a computer can do billions of times per second. Something computers cannot do fast, or easy, or in most cases at all, is symbolic math. So maybe now you can kind of see the vision. We use these algorithms to implement them into the computer, which can do them very fast, which gives us an approximate answer very, very quickly. This brings us to an important aspect of numerical methods, the accuracy versus computation trade-off. If we use 4 rectangles, our answer is okay. If we used 8 rectangles, our answer would be better, meaning we get less error when we use 8 versus 4 rectangles. But it'll take us twice as much math, and therefore twice as much computation time to actually get to that answer. Imagine the computation time just being the amount of work our computer has to do to get to the answer. Expanding upon this, if we used 1 million rectangles, our answer would be very close to perfect, but it would take our computer much longer to run to actually get our answer. Numerical analysis is the art of balancing this trade-off, so getting an answer that is accurate enough for your application in the shortest amount of time. This is something we will talk more about throughout the course. Now that we have a broad understanding of what numerical methods are, what type of questions can we actually solve using them? Throughout this course, we will talk about many of these approaches, including some root finding, numerical integration, numerical differentiation, solving systems of equations, optimization problems, numerical interpolation, and solving both ordinary differential equations and partial differential equations. Although the majority of these problems can be solved using either numerical or analytical methods, we can make our lives so much easier by selecting the correct approach from the start of the problem. We typically use analytical methods when the problem is simple or linear, you need an exact solution, so if you're working out a math proof, for example, You want to see general trends, like maybe how one variable affects another one specifically. But we use numerical methods when the problem is more complex, nonlinear, or a large linear system, or has no analytical solution. You're dealing with massive systems of equations, like simulating weather patterns, airflow over a wing, engine block design, anything like that. And when we deem an approximate answer is good enough, which for most real-life applications is what we use. In conclusion, analytical methods use symbolic formulas to find the exact solution. But these methods are often difficult or impossible to solve, and are best reserved for simple geometries with low dimensionality, or when we need exact answers like a mathematical proof. On the other hand, numerical methods utilize computers that are very good at repeating simple math very fast. They do this through the use of algorithms and iterations to approximate solutions, which for the upper majority of problems is acceptable in what is used in real-life applications. Thank you for watching this video, and I hope it helped your understanding of the key differences between numerical and analytical methods. If you enjoyed, please like, subscribe, and consider checking out our YouTube memberships by clicking that join button down below. However, if you have any comments, questions, or concerns about the information I presented in this video, please leave a comment down below, and I will do my best to address your concerns.